Hey, oh shit. Do you want your process time in Godot to go from this to this? Well, slip on your programming socks because we're about to start cooking with gas. And hello there, it's your boy, charmedimsure.
Charmedimsure, I'm Gilfasan.
So, what's this performance boosting meme I'm selling you? A data-oriented design entity component system. That's right, performance can be yours for the low price of maybe having to debug seg faults. Who knows? So, what do all these fancy $20 words mean? It's actually pretty straightforward. Data-oriented design means designing programs around the data one expects to be processing. And entity component systems means a system of entities and components. The two go together like peanut butter and jelly. Under the proper conditions, they run laps around anything else you could think of. I'll note that this is a somewhat advanced topic, so if you're only familiar with GDScript, that ain't gonna cut it. I implemented the demo for this video using GDExtension and C-styled C++, since I am hopelessly addicted to pointer arithmetic, even when I get it wrong and cause a seg fault. So, if you're unfamiliar with GDExtension, there's a link in the description describing how to set it up for a Godot project, along with a link to the repo for the project in this video. But as I said, this is somewhat advanced. We're not hopping into assembly here, but I'm going to assume you have a familiarity with C++. So, as you can probably guess by its name, ECS is similar to composition, but cranks it up to 11. Data and behavior are completely segregated, for better or worse. The canonical example for ECS is projectiles. So by comparison, a regular object-oriented projectile would have fields describing its speed, position, and lifetime, and a method to update all of that data appropriately. Whereas in an entity component system, the eponymous entity may have any component. It may have no component. It may have every component. So for a projectile, an entity would only need a position component, a velocity component, and a lifetime component. While this may seem clunky at first glance, it has niche advantages. Like anything, it has its trade-offs, which I'll get into at the end. Also, important note, there are a myriad ways of implementing ECS, so if you see something different, just keep in mind that a rose by any other name is still a rose. So the example, projectiles. The straightforward approach is to just instantiate and free the projectiles as needed. I set up an example scene doing exactly that. It's set to have 1000 on-screen tops, so let's give it a whirl and see how badly OBS messes up performance. Wow. OBS is really messing up performance. I ran this before I started recording, and I was getting about 170, 160 frames per second. I forget what the average process time was, which is what we're looking at in this graph. Unfortunately, I sort of expected this. I don't have a GPU. I am just using my laptop's CPU's integrated graphics, so it just really do be that way sometime. But this works even with OBS running in the background, so instead of 1000 projectiles, what happens if I increase the number up to 10,000? And as we can see, I'm in the single digits frames per second. This is not acceptable. But you're all sensible game developers. At 10,000 of any of the same thing, you'd start pooling your nodes and using a multi-mesh to render all those doodads. And I've done exactly that in this next scene. But as you can see, performance does not improve. So let's get down to brass tacks. I've written out everything ahead of time, and I'm just going to talk about it because, boy howdy, this was more substantial than I expected. Now keep in mind, this isn't just any old entity component system, it is a data-oriented entity component system. So before any of the ECS stuff, I ensured that all of my components and basic entity data were allocated contiguously in memory, which is a fancy way to say that they're all just in an array. That's the secret of data-oriented design. Just use arrays and avoid branches. So before anything else, I wrote a couple custom allocators. The first one is just the classic arena allocator, but I added a cute little scratch method since I reused the memory itself. Next, a pool allocator, which allows me to allocate and reuse components super easily. I'm glossing over this a bit since it's not the focus of this video, but if you want to know more about custom memory allocators, the creator of Odin, gingerBill,
You've caught me eating some cheese and crackers. There you go.
wrote a great series of articles about them, the link to which is in the description. But it's important to note that just like ECS, these allocators have advantages and disadvantages, and I chose them for their respective strengths. One thing to note is that since I have a 64-bit OS, I used 4-byte indices for my pool instead of pointers, so that way my smallest components can be 4 bytes, meaning I can allocate floats and 32-bit integers. Another important thing to note is that I've designed my pools so that free uses a ZII-inspired branchless conditional to handle freeing pointers. It's definitely memey, but I think it's hot, and I'll show its value later. With allocation out of the way, let's get to entities. And what exactly are entities? They are general-purpose structs or objects that exist just to be associated with component. I needed a way of tracking all the entities and which components they have. So I used a struct of arrays, which I'm calling the ECS table, to track the addresses of my entities, which components they have, and the addresses of the components themselves. I of course used a bit mask to track whether or not an entity has a component, meaning with this implementation I can have at most 64 components, but for this demonstration and for more purposes, I think 64 is more than enough. But if you do find yourself needing more, I don't know, reach out to me for contract work. I'm no stranger to W9 forms. The entity table is a global stack variable, so it just exists, and I initialize it using the ECS constructor function. And the ECS class, it really should be a singleton, but it's not. I'm not opposed to singleton. In fact, singletons are fine. They have their place. I'm not opposed to them. Finally, when I want to make an entity into a projectile, I just register the entity in the ECS table and then keep its index because I use that to add components later. As for the entities themselves, they just cache their index in the ECS table. That's it. As you can see in this class, there's absolutely nothing, no updating, it's that simple. Next, components. Again, also super simple. Components are just some data. For my projectiles, I'm going to have components for position, velocity, and lifetime. 3 dead simple structs. I initialized all the pools for the components in the ECS constructor, and I already set up the pool allocators, so again, I can just turn my brain off here entirely. So after I registered an entity in the ECS table, I use its index to allocate its position, velocity, and lifetime components, and flip the appropriate component bits in the ECS table. And for the final word in the ECS acronym, system. My brother in Christ, this is the system. I got my entities, I got my components, that's it. No more letters, no more words. All I gotta do now is update the component data appropriately. So how do I do that? I have a master plan I'm following for this video, so I did it in a particular way. But it's very basic, and I'll walk you through my position update logic to demonstrate it. So if we look at the ECS class's process method, first I determine which entities need to be updated, in this case all entities with a position and velocity component. As you can see, the bit mask is kicking right here. Next, I gather all the appropriate component data into a single contiguous array of memory, so it's cache friendly. Basically, I just copy all the individual structs for position and velocity into a single struct of position and velocity, ensuring all that data is packed in real tight. And I also allocate an array for any resultant data, in this case the new positions. And again, this is all just to appease the CPU cache line. Next, I perform the appropriate transform. Super simple. The new position is just the old position plus delta times velocity. Finally, I copy the resulting data back to the appropriate components and move the actual node. But all in all, nothing fancy. The only difference is I'm working in bulk instead of individually. And I'm updating lifetimes using the exact same process. You can look at it, I think it's just as straightforward. The only important thing about lifetime data is that I also use it to free entities and their respective component data. Now, in order to actually free an entity and all of its associated components, I exploited the components bit mask from ECS table. I did not want to add data that I didn't need, so instead of creating a wasteful Boolean component to decide whether or not to free an entity, I just declared a quick and dirty macro to sub in free entity for num components. My only concern with doing so is that it tacitly decreased the number of components representable in the table by 1. But the advantage of this is that I use a similar process to free entities as I do when updating components. I'll pop the code for this on screen real quick and explain it, but I think it's relatively straightforward. Again, first figure out what has to be freed, free the components, return the node to its pool, and finally swap out the freed entities from the ECS table. And no need to check for null when freeing components because pool free does that branchlessly. And to finally tie freeing back to lifetimes, I changed the lifetime struct into a union with an unsigned integer so I could do this memey trick after updating them. This is based off the definition of a float to use the sign of lifetime to do a cheeky little bitwise operation and just flip a bit. So with all that set up, it's time to give this a whirl in Godot. Again, 10,000 projectiles. Let's see how badly OBS is tanking my performance. And would you look at this? We're hitting 10 frames per second half the time. Yo, was that 11? So yeah, ECS kicking it. However, 10 frames per second is just as bad as 5. Hate to say it. So backing away from this extreme case, if we go back down to 1000 projectiles and compare ECS against the projectile spawner, I'm actually getting about 10 more frames per second. Not too shabby. And for the final part of my master plan, you keen-eyed developers may have noticed that all of my component updates are, to quote Mr. Bobrov, embarrassingly parallelizable, which is one of the niche advantages that data-oriented design and ECS offers. Since everything I'm working with is just an array and each individual component update acts upon its own segments of memory, I can just multi-thread it, period. No need to use mutexes, atomics, semaphores, nor worker pools, and no need to worry about race conditions nor deadlocks. I'm even using threads.h instead of platform-specific threads since I'm already late for this video and I want this project to be as portable as possible. I just divide update arrays between threads using basic fan out and fan in. Even freeing entities is partially parallelizable since I wrote it kinda funky, but instead I divide the work amongst my threads component-wise instead of entity-wise. Otherwise, I'd definitely have to use a mutex while freeing the components since individual threads could simultaneously write and read from the same memory. But unfortunately for the swap and shrink, that part is not Grug-Brained parallelizable, so I'll leave it single-threaded. And in that vein, massive asterisk right here, if you are adding and removing components while multi-threading, you will have to design around race conditions. I think data-oriented design specifically is extremely multi-threading friendly since for the most part, I don't have to think. As you can see from the code, it's just fan out and fan in, fan out and fan in. So 10,000 projectiles, let's give this bad boy a spin. And honestly, I can't tell by these numbers if it's better. Maybe it's a little more consistently over a 10. I can't tell. Creating a thread has its own overhead, so it's not just free performance. But I think the real problem here is my integrated graphics. And my laptop cannot just handle this at all. So I'll hide the node meshes and rerun them both. And looking at the side-by-side comparison, I can't really tell which one's better. I think this is something you'd have to rigorously test. It probably varies on your own use case as well. So single-threaded, multi-threaded, they both might be fine, or I'm bad at multi-threading. Who knows? But what if I told you I can get better performance if I increased the number of entities? So I'll raise the number of entities from 10,000 to the entity cap, 65,536. And if we look at these numbers, the frame rate has tripled. I'm not pulling a fast one on you. I can mouse over the nodes in the scene. It's over 65,000, yeah. So this sounds insane. I am getting a 3 times performance while I am processing over 6 times the amount of data. This sounds insane, but this is the power of data-oriented design. Your computer can absolutely blitz through all the data you present it if you do it right. In this case, the entity table is completely utilized. The stars and the data are aligned and your CPU loves it. This is getting a little too into the weeds for this video, but you should read the Data-Oriented Design book by Fabian. The link to the web version is in the description. It's amazing. Again, 3 times the performance on 6 times the data. The numbers don't lie. And obviously I could have kept trucking and tossed in SIMD. Update positions is prime for it, but I won't. Instead, it'll be more valuable if I talk about why I designed everything the way I did. First off, and most obviously, why is the basic spawner pretty competitive at small numbers? I'm copying a lot of data, which takes up time. So why am I copying the component data to the argument memory, then dumbing that into the results, then copying that back into the component data? Again, it's to mostly cut out all of the chaff from the bandwidth and really pack those cache lines in tight. And as an added benefit, it makes multi-threading easy. And ECS as a whole, I think it shines when used for at least thousands of entities, especially when it's being stapled onto an existing system like I'm doing so here. But as you can probably guess, if there's only one of something, say a player character, then what's the point? Also, it is kind of challenging to implement complex behavior since you have to decompose it into simpler parts. Hey, I'm mid-editing and I forgot to mention that while I'm just comparing projectiles, a real advantage of ECS is that again, components are just data and they can be added to entities freely and dynamically. So if I wanted to, I could easily create components for health and damage, then create an update to act on those components super easily. And again, just toss everything into the ECS class, which you can see me do in the background here. Again, if you like this, hey, if you don't bother.
Alright, let's see what happens when we press play.
And no segue, but on the subject of memory usage, ECS components are just hands down better. Since nodes are classes, they use more memory since each one has its own vtable, whereas ECS components take all that junk out of band. So on this metric alone, components win. But since I also used a pool, the memory for components is allocated once and then recycled and reused as needed, which admittedly you can match by pooling objects. However, again, one allocation, so it's all contiguous in memory instead of individual RAII nonsense. So as I've been saying throughout, it's way more cache friendly since it's not thousands of allocations coming from God knows where. And there are undoubtedly other design decisions that may seem weird to you that I didn't bring up, so please ask away in the comment section and I'll get back to you. And I'll give myself an easy out. There are probably better ways to design this system that I overlooked, and again, maybe I screwed up the multi-threading. I hope not, but I would not be too surprised. And that's it for this video. As I said at the top, you can find all the source code for this repo in the GitHub link in the description, along with everything else I mentioned in this video. So as always, thank you for watching. I appreciate your time and I hope you have a good day. If you liked the video, please give it a like. And if you want to see what's next, please subscribe. I think the next video will be an introduction to C macros, because if you check out the repo, I use them throughout the code as a metaprogramming tool to generate functions and enums and create the appropriate GDExtension bindings. I think they're actually super simple and insanely powerful, but most people only use them to import headers and pragma once. They're truly slept on. So I think they're great, and fingers crossed it'll be a nice, easy video to make, which is what I want after this doozy. And what else? There's also a Discord server for the channel where you can talk about game dev, programming, math, cooking and baking, and oh my god, please post memes in general. I love memes, as you can tell by that pool free. Oh, look at this function. I love it. It's memey, it's hot, it's sexy, beautiful, love it. And you know what else I love? Baking. So let's get to it. Oh my god, I'm losing my voice. I've edited out a bunch of parts during the the 65, the 2 to the 16 bits. That was just, I edited out segments that were just me shouting. I was losing my mind. I'm surprised I'm really good. I mean, the first time I saw that, I did a triple take, because I yeah, I think I did when I tested it. I went from 50,000 to that number. I was like, okay, I'm getting like 8 frames per second, and I'm like, all right, I'm getting like 1,000 frames per second. I was like, what? So yeah, it was just honestly, I had an inkling that was going to happen. I didn't know it was gonna be that good. Honestly, I'm surprised. I'm really glad OBS, even with OBS weighing it down, it still performed exactly how I expected it to. Again, it wasn't like from 100 to 1,000, but still, like I'm happy. It's still good. 3x, yeah, I'm pleased. Anyways, classic. What do we got? Sourdoughs. Yeah, let's keeping it simple. Oh god, where's my water? Jesus. Anyways, So yeah, I'm gonna cut this. I'm gonna be a little briefer than usual since I don't have to pad out the time on this video. But yeah, here we got some 2 gorgeous looking sourdoughs. Let me double check if I have any notes. I don't think I do. No notes. No notes. But as you can see, if we go take it back, look at them. One's a brunette, one's a blonde, sort of blonde. Maybe it's a dirty blonde. Who knows? I mean, I love me some bread. Brunette, blonde. I won't complain. But again, and if we take a look, and again, I'm not doing the cross section here. Because again, I do think I didn't get good ears on these. Don't ask me why. If I don't have notes, but I would assume this might be an 85% hydration. I tend to not get as good ears the higher hydration I get because again, gluten formation becomes a little trickier. But if we look at the cross section for one of them, again, yeah, this is where it looks like a higher hydration Godot, so that's why I guess this was 85% hydration. And again, yeah, that's why I tend not to, and you can tell it's higher hydration because again, there are these just ginormous bubbles in there. That's all the steam, just all the water in the bread turning into steam and making it rise. Honestly, it looks great in photos, but if you're like trying to smear butter on there or something, it doesn't work out that well. It does not work out that well. So for like a good sandwich bread, you want to or a good sandwich sourdough. Like if you imagine putting butter or like any kind of spread on it, I would say stay in like the 75% hydration. Yeah, it's great because you get a little tighter crumb, which look, it's gorgeous loose crumb. But again, like you try smearing butter on there, it's going out through it's gonna melt through the holes. Absolute no go. But for dipping olive oils, or dipping in olive oil or balsamic vinegar, it's a great 85% high hydrations are great for dipping. Or, if you put cheese on there, cheese is great on any kind of bread. Let's be honest. I kind of lactose intolerant. I can eat cheeses though. So, cheese? Cheese. Oh my God, I'm exhausted. Jesus. But yeah, so I'm tired. I'm going to cut it here. But yeah, I hope you enjoyed this video. And I can use the classic sign of absolutely guilt-free. The yeast in the air is free, so go out there and bake. It doesn't have to be bread, but you need yeast for bread. And don't get me started with flatbread. It's not. It's fine, but come on. If there's no yeast, sign off. The yeast in the air is free, so go out there and bake. It's nutritious, it's delicious, it's good for you, and it makes a great gift to show people that you appreciate them. And I appreciate all of you. Thank you for watching, and I will see you next time.